Hi, I am the business representative, Professor Horiuchi from Electrical Engineering. The exam consists of two parts. The first part is the open part and consists of presentation by Douglas and questions from the audience. After that, we would ask the audience to leave the room, and we will continue with the second part of the exam. So, that's this.
All right. I'm going to discuss automated image comprehension. So, image understanding has always been a goal of the computer vision community. This is one of the major journals. But when you talk about understanding for machines, there's some philosophical issues there, right? Is it really possible for a computer to understand things? Well, people have brought up qualia and consciousness, and there's Searle's Chinese room argument. So instead of trying to say whether the computer is understanding, what we can do is say, how do we test whether people understand something? How do educators measure whether a student is understanding? And apply these same tests and try to build a system that's able to pass those same tests. So that's what I've tried to do. So this is Bloom's taxonomy. 1956, educators got together and discussed how we could categorize the types of questions that you can ask. Before that point, education was mainly focused on here at the bottom. There was a lot of emphasis on rote learning and knowledge type questions. And they wanted to move the focus up here. Now, at the top of the pyramid, this is questionable, right? Is evaluation really more difficult than synthesis, or is it part of it? I don't know. But down here, it's pretty solid. The knowledge is the easiest thing to automate. We do a lot of this in computer vision. Identify, match, reproduce, recall, define. But my focus is to try to solve these problems. To describe what's in the scene, or condense what's in the scene, interpret it, discuss it. So what needs to be built in order to solve those kinds of questions? And what needs to be in the system has been understood for a long time. This is Dewey, who invented the Dewey Decimal System. In 1910, he says, to grasp the meaning of a thing, an event or a situation, is to see it in its relation to other things, to notice how it operates or functions, what consequences fall from it, what causes it, what uses it can be put to, as opposed to direct knowledge, which is simply being able to repeat something without understanding how it connects to everything else. So, how I've attempted to do this is to describe the scene using concrete nouns, verbs, and adjectives. So this is a little bit metaphorical. I'm talking about objects, materials, and activity recognition. But it's easier to think of it as making sentences and putting these sentences into a knowledge base where it can be tied to all of the other information that we know about the world. So, go ahead and read this. Example, and then I'm going to ask a few questions about it, and see if you can answer these questions. There's a car made of metal, glass, and rubber. Already that's a little bit weird, right? We all know that cars are made of metal, glass, and rubber. I don't need to tell you that. Anything that's already in your memory, there's no point in restating it when I'm describing the scene. The car is on a gravel road. The road is near some grass. There are trees near the grass and car. There's a person near the car and a metal object. The sky is above the trees. The person is changing the tire on the car. So, first question is, are there any windows in this scene? How do you know that there's a window in the scene?
Because you know the cars have windows and there's glass.
That's right. The car always will have window. The car has a part made of glass. We know that the car has a window. Is there anything flammable in the scene? Well, there's some trees, and trees are made of wood, and we know that wood is flammable. Are there any octopuses in this scene?
No.
There's no ocean, and we know octopuses are always found in the ocean. So we can be pretty sure there's no octopuses in the scene. Here's the actual scene. You'll see this again later because I used this for some of the actual runs of the program. So exactly what we were doing, using our knowledge of the world to infer what is happening in the scene from the description is what I've built the system to do. So there's 4 parts. First, recognizing objects in the image using scene classification. Second, recognizing the materials that objects are made of. This is very similar to how the object recognition is done. Action grammars are a way of recognizing human activities, and all of that is put into this research site knowledge base, which contains a lot of world knowledge that we can then ask questions, and it can tell us the answer and how it arrived at that answer, the chain of reasoning that allowed it to arrive at that answer. So each of these parts I've done some of the development on. I've advanced the state of the art on each of these detection methods, and I'm going to proceed through talking about these first, and then talk about how to solve the problem. First, scene object classification. So this is an example of what's known as scene parsing. About 2003, people started saying, not only can we recognize objects in an image and put a rectangle around the object and say that's where the object is, but we can actually label all of the pixels in the image and say what class each of these pixels belongs to. So in this case, brown stands for leaves, green stands for grass, the dark green is for foliage and trees, and white is for a building. Oh, blue for the sky as well. So it's done a pretty good job of picking out what class everything belongs to.
Sorry, can you repeat what the white was?
White is for buildings, human-made structures. Actually, this program can also identify sidewalks and streets as well, but there's none in the scene. This is scene classification. You can notice there's kind of a mix. Identifying this as leaves, really that's more of what the material is. It's underbrush or something like that. It's labeling this as a material, whereas buildings, that's identifying an object. So scene classification has always been a mix of object and material classification. And one of the things that I've done is separate those so that you can now identify all of the objects in the scene and also all of the materials in the scene. So when you put those together, suddenly you have you can multiply the number of things you can detect. If you can detect 10 objects and 10 materials, there's a potential of identifying 100 different material object combinations. That's why it's called productive vision, the product of those two. So for doing the object recognition, the scene classification for objects, we came up with what's called visual filters. So first we collect features from an image. In particular, these features are a pyramidal RGB patch from the image. We collect maybe 1 million or even 10 million is the most I've done. 10 million of these samples from many images that have examples of the object to be recognized. And for each sample, we have we have the original image and a mask showing what class everything belongs to. So if it happens to randomly choose this spot to take an example, that spot's inside the person. So it says the patch that looks like this should have the label person. Those patches are then compressed using PCA to maybe a 100-dimensional vector, and those vectors are used to train a classifier. The particular one I've used most often is just a single layer perceptron classifier, but we've tried several other types. And with that, we run the classifier on all of the training images. So the classifier then tries to label each patch in the image using a convolution, a filter, where it looks at each patch one at a time and assigns a label to it, the probability that it belongs to each of the classes that we're looking at. So you get a result that looks like this, and it's not very good. It's a low quality estimate, but it is better than the original estimate, which was that everything has an equal chance of belonging to any class. So then what we do is we go back again and we gather samples from the training images, and also at the same time take the sample from the first estimate. Again, a pyramidal patch feature from this first estimate. And what that allows us to do is use the estimates from neighboring pixels to influence the estimate for this particular pixel. So if you've heard of the auto context algorithm, that's doing a very similar thing. It's learning to recognize from the context what label a pixel should have. It does this again and again, maybe 3 or 4 or 5 times, until it stabilizes and stops improving in performance. And the final result is a higher quality estimate of the labels. So here's some examples. This is the ground truth, and this is the original image. This is the first iteration, second, third, fourth, and fifth iteration. Each time it's getting rid of some of the misclassifications. The black area is back here where it thinks a person might be in that area, but it decides eventually no, that it's unlikely to be a person.
So is the filter a person filter? Is that?
That's right. This particular filter is a pedestrian detection filter, pedestrian versus background. This one is for horses versus background, and trained only on horses. This is the pen-fed pedestrian data set, and this one, Wiesmann horse data set. All of these horses are seen from the side view, so that makes it a little bit easier.
Is there single images or are they movies?
Single images. So that each of those was only 2 classes, but traditionally in scene classification you get something like this, where you have a scene of the city, and then you label 5 or 6 classes within the scene: sky, street, cars, buildings, trees, and pedestrians. I think is the blue. So the visual filters can be used for this task, but we also explored other ways they could be used, which people generally don't use scene classification techniques for. For example, limb classification, recognizing where someone's limbs are. This is a sports action data set, and it was trained on other examples of people playing these same sports. You can see it's done a fairly good job of pulling up where their arms, torsos, and legs are. It uses the context that arms are usually found near torsos, legs are usually found below torsos, heads above torsos, in order to improve its estimates as it does each iteration. Another thing that these visual filters can be used for that other scene classification techniques don't work for is for semantic edge labeling. So people went through and hand annotated where are the important edges in several of these images. And then this was trained on those handmade labels and used to try to mark up the important edges in these scenes. So this is a traditional edge classification technique based on just the orientation and the strength of the difference between neighboring pixels. And you can see it picks up lots of edges that aren't very important. Here you've got a lot of edges in the grass that just aren't very significant. But in this image, it's found that this is the main important edge that people would care about, that separates things which are semantically different. And here, it's pulled out these soldiers. It even pulled out this soldier up here. It's pretty well hidden in camouflage.
So this, I mean, you have to assume something about tasks.
Yeah, so
If your job was to describe the terrain, you would have drawn a different set of lines.
that's right. In the instructions that they gave the people making the labels, they just said, find the important contours and mark those out. So this is trained to do something similar to that. Another thing that you can use it for, along the same lines, is if you were doing normal scene classification and you're trying to detect pedestrians against background, these pedestrians who are right next to each other would just show up as one large black region in the image. But with training it not only on the regions but on the edges surrounding each of the individuals, we can create labels that also have edges around the figures. And that might help us to separate them. Okay, next is material classification. And this could be done in using the same method. But there's some reasons to think that we can do a little bit better than just applying the same method. So in the last few years, a few people have tried to solve this material labeling problem. But they applied it to whole images, saying this whole image, is this a picture of something made of glass? Is it made of wood, and so forth. So the main thing that I did differently was to say, let's break up the image into different pieces that seem to belong to the same